Hello, everyone. My name is Lacey Stachel, and I am the Marketing Manager of the Slag Cement Association. I'd like to welcome you to today's webinar, Geotechnical Applications with Slag Cement. We are glad you could join us. Attendees are in listen-only mode. You may ask questions using the dialog box in the GoToWebinar software. Our speaker will be happy to address any questions at the end of the presentation. The ideas expressed in the following presentations are those of the speaker and do not necessarily reflect the views of the Slag Cement Association or its committees. As with all concrete mixtures, trial batches should be performed to verify concrete properties. Results may vary due to a variety of circumstances, including temperature and mixture components, among other things. You should consult your slag cement professional for assistance. Nothing contained herein shall be considered or construed as a warranty or guarantee, either express or implied, including any warranty of fitness for a particular purpose. This description for today's webinar is shown on the screen and also listed on the SCA website with the webinar series information. Now, I'd like to introduce today's speaker. Gordon McLellan is Technical Manager at Lehigh Hanson Slag facility in Cape Canaveral, Florida. He has been involved in the development and growth of slag cement, formerly known as ground granulated blast furnace slag, in North America for 28 years. After Queen's University, he worked with Coke Minerals in Sudbury, Ontario, Canada, developing applications using slag cement in mining, backfill, and geotechnical applications in heavy construction. As a product manager for Wholesome in both slag and fly ash, where he started in Chicago, Illinois in 1993, he continued promoting the use of slag cement in concrete applications. Gordon is now living in Cape Canaveral, Florida with his wife Cheryl, where he joined Civil Marine in 2003 during design and development of the Cape Canaveral slag facility. As a technical manager, he oversaw product development, then sales and marketing. The Cape Canaveral slag facility was later acquired by Hanson plc and became part of Lehigh Hanson, followed by Heidelberg Cement's acquisition of Hanson plc in 2007. At this time, I would like to hand it off to Gordon.
Good afternoon, everyone. I'm looking forward to this. So I look forward to some good questions. Next, please. Next slide, please. Perfect. That's going to work great. I'd like to start just by talking a little bit about slag cement and specifically slag growth in the USA. As you can see, we're approaching 4,000,000 4,000 metric tons of slag with some fairly amazing growth over the last 4 or 5 years. In fact, it's fair to say we've doubled since 2010 in product and product availability. And for various reasons, I would like to think that it's mainly the high performance and the environmental concerns driving us towards using more slag cement. Next, please. I always like to start briefly with where slag cement comes from. And I think if you've followed some of these other webinars, they've gone into this in a little more detail than I'm going into. I just want to kind of briefly touch base so that we understand the difference between slag cement and blast furnace slag and answer other questions potentially about fly ash. But I like this picture because it starts off with the manufacturing of Fe in a blast furnace. And I view a blast furnace as a vertical kiln, in that everything that would go into a Portland cement kiln is added to the blast furnace, albeit in a little different proportions, but the basic materials are there. So the main difference is that the finished product, the slag, which is floating above the Fe, can be characterized more as a dicalcium system. What we're really missing is the C3A and C3S that we find in Portland cement, but everything else is there. Another way to look at it is typically calcium in Portland cement runs 60 to 65. Calcium in slag tends to run between 38 and 42%, and most fly ash is below 10. So the fact that slag cement can be viewed as a hydraulic cement shouldn't come too much as a surprise when we look at the genesis, where it's coming from, with that vertical cement kiln versus the horizontal cement kiln. So let's look at what happens to the slag floating on top of the Fe. Next, please. I love this picture. It's the color more than anything else that to me, it is energy. We are showing energy. In this case, for the most part, this energy is wasted. The slag is coming out of the blast furnace. We're letting it air cool, and it's turning into an aggregate. Now, it's fairly common to see concrete paving around most of the steel facilities in North America is made with blast furnace aggregate. It's a perfectly fine aggregate. It's air cooled. It is slightly more porous, so our concrete guys have to know how to handle it to make sure the aggregate is soaked and so forth to deal with that, and it makes perfectly fine concrete. There is, however, a higher value that can be assigned to that material if we process it a little further, and that's really what we're talking about today, is how we make a higher value product. Next, please. And this is the journey of turning slag into cement. What you see here is the granulator. The purpose of the granulator is to impinge high amounts of water to turn it into what you're seeing in that gentleman's hand. If you look closely, you can see little whiskers. And in fact, it is between 90 and 93% glass. That's the purpose of taking that material from its molten stage and turning it into the raw material for slag cement. So in the past, we used to talk about granules. This is granules, and slag cement was referred to as ground granulated granules. The raw material here, next, is ground into a hydraulic cement. The first thing that we can see, obviously, is it's very light colored and looks much like white cement. Next, please. So, what is the differences between Portland cement and slag? Well, as I said earlier, the cement is typically manufactured with the use of a kiln, requiring high heat and some virgin materials to produce a clinker, which is then ground into hydraulic cement, versus slag starting out as a recycled waste material. What you saw in that molten form, we've now processed it slightly more to turn it into glass, to turn it into a cement. That process uses less total energy and has no carbon associated. The carbon is associated with the making of the Fe, and this is looked as a recycled material, driving some of its increased use around the world. So the other aspect, and again, I'm not going to go into all of the details, because if anybody has watched some of the other webinars, they've gone through and listed the numerous advantages of slag and ready-mix concrete. The purpose of this presentation is more to focus in on the application of slag cement into a geotechnical application. So really the two things that are most important is the higher compressive strength at 50% and the far lower permeability. That's what we in the geotechnical world care about. Next, please. So PSI per pound of cementitious. Slag cement is more hydraulic in lower amounts and higher water cements than Portland cement. That's a relatively easy sentence, but I always like to give a little color to it. When, one of my first geotechnical application was slag cement in mining backfill, where we were replacing Portland cement with slag cement to achieve low strength fill in these vast chambers underground. And the last project I show will deal a little bit with that, but not getting ahead of myself. The interesting thing in that first application was that we went from 100% Portland cement to 80% slag, 20% Portland cement, and we reduced the total cementitious by 50%. There was a huge savings in that initial replacement, and we're going to deal with why we could do that. But for the purposes of this discussion, I really want to tell about the first phone call I got after the application of this material underground, and it went something like this: you have solidified all of our sumps in our mine. What I'm saying is the call was, whereas at more cementitious and no slag but Portland cement, the material would work its way into the bottom of the sumps, and because it was in small amount quantities, it was just handled as a normal fluid. Slag cement changed that. Even at very, very small amounts, there was enough there for the cement to actuate and solidify the slag. So we quickly realized it was working, but we needed to do something to keep the slag more in the chambers. And in this application, we just added a flocculant, so it settled out a little quicker, and we were able to keep more of the cementitious where we wanted it. So, therefore, as strength requirements lower, slag has a more defined effect than Portland cement and is used at higher replacements, sometimes greater than 70%, and of course requiring less total cementitious. The next point in geotechnical applications is that we're looking at the toxicity. Slag cement is less toxic as per TCLIP data that we'll get into. Very important when we're looking at Superfund sites where we're using the cementitious material to capture heavy materials. So it does have the ability to tie up heavy metals, similar or higher compared to Portland cement. And of course, once it solidifies, has much lower permeability than PC by itself. So that when we do these job sites, we can then monitor the leachate coming out of the project and prove that that we actually have contained the target material. Next, please. So focusing on toxicity, TCLIP is kind of it was the gold standard, and the picture I'm showing here is I'll ask everybody to forgive me for being humorous with regard to TCLIP, but that is a picture of a fish floating above granules. In the original testing, the toxicity was determined by fish that had to live for a specific amount of time in the leachate coming out of off the target. So we brought this into a presentation we were giving at a Department of Transportation. We called the fish Little Charlie, and it was our kind of graphic representation of the fact that slag cement is considered very appropriate in this application. So, next slide. The details behind that are shown here. So here we have heavy metals: arsenic, barium, cadmium, chromium, lead, selenium, and we're showing the typical results we see. In most cases, non-detectable. Barium still very low, but the limit obviously is substantially higher. So this is one of the reasons why we're involved in so many geo projects where they're trying to capture or tie up elements in the ground. I would also add that one of the elements we're missing here that has come up and we've gotten some attention over the last 5 years is aluminum. Aluminum is not a heavy metal. It's one of the most abundant metals in the Earth's crust, and it's very light. So typically it was not viewed as a target element. Now there is some discussion about aluminum and toxicity and potentially contributing to Alzheimer's and other things, but that data is still a work in progress. We don't test for it. In some of the sites we're at, in the test wells, they do monitor it, and when the job is done right and that we've tied up the concrete, or sorry, tied up the soils appropriately, we don't see anything moving through the ground because of the very high very low permeability we've achieved with slag cement. Next, please. So moving on from that discussion to what we're seeing in the field. I'm going to talk about 4 projects that we've done over the last few years that I think are illustrate why slag cement is being used in so many geotechnical projects. The first one is Lake Okeechobee in Florida, and you can see the picture of it. Obviously, one of the largest freshwater lakes in North America, or certainly in the U.S. And there is a dike that was constructed in the early 1900s, was refurbished around 1937, and then been virtually unchanged. And the concern was that we were starting to see seepage coming through the dike, and many discussions were had as to how to solve this problem. And the winning approach was a cutoff wall down the center of the dike. And the dike, I think, is 147 miles long. We started this in the mid 2000s, I think 2006. The next slide will document that. But with very interesting results. Next slide, please. So, as I said before, let's look at that. 143 miles. I was wrong. We started this project in 2006 through 3 contracts, each worth $250 million. We're now in the last phase. We currently have 6 task orders or sections being completed. The whole entire project is fast-tracked and should be finished by next year. And the goal is to have the dike able to handle the higher waters and stop the leakage that was occurring through the dike. Now, so we have 3 contractors on site right now. They're all using a mixed design that is approximately 75 to 80% slag and 20 to 25% Portland cement. Next, please. So all variations on a theme. What we're looking at is, most of you have seen hydromills, cutter soil mixers, or TRD machines. Ultimately, what we're doing is mixing a cement slag slurry with the existing ground conditions, allowing that to solidify, looking for relatively low strength, 500 to 800 psi, but looking for very low permeability. And that's the reason why that mix has gone to such a high proportion of slag cement. I like to look at it for every linear foot of dike. They're using, depending on the process and whether they add additional soils to the ground or not, anywhere from half a ton of slag cement to 1.5 tons per linear foot. So extremely huge project. Next slide, please. And again, another look. This is the TRD, which currently is not being used, but I did like this system, and it is being used in other places. You can see it's basically a chain and cutter with the soil, the cement, bentonite, slag mixture being injected into the soils. Next, please. So this project, when it first came out, we really wanted to look at it carefully and make sure that we were supplying enough technical information. So this is one of our first lab studies that we did, comparing 100% Portland cement to that traditional 75-25 slag to, in this case, we also wanted to push the envelope and see what a 100% slag cement would do in this application. Again, kind of trying to earn our designation as a hydraulic cement on its own. And the data is quite interesting. You can see that in most cases we were doubling the straight cement strength. And in these applications, you know, this is not ready mix concrete. Typically we're looking at between 300 and 600 as the target strengths. It can vary up to 1,000 on some geo jobs, but typically that's the range. So in this application, we probably could have used 100% slag to achieve something that would have been acceptable, in this case, better than Portland cement. But that is also because of the other mixtures that was going on in the soil and so forth. Next, please. Moving on from that, I had mentioned aluminum before, and when we were talking about T-clip data and so forth. So we are seeing now slag cement varies with alumina levels from 8% to 15%. And we wanted to see the difference that alumina would make. In general, alumina helps us from a compressive strength perspective, and this data kind of supports that as well. So you can see the high alumina plus GIP. So we are now using calcium sulfate or GIP at about 3% with our product, and most of the producers of slag cement do that. And you can see some of the effects that has on early strength and even latter date strength. So we originally tested with moderate alumina, and we ended up over the last 10 years moving to a high alumina plus GIP. High alumina, as I said before, being 14% alumina. Well, specifically 12 to 14% alumina plus 3% calcium sulfate, and obviously with very, very good results. Next, please. So moving on to another project. This is the Miami Access Tunnel. This project was 5 years ago. I'm sorry, I don't have the exact time for that. But next, please. Slag was employed on this project in two ways. One, in the geotechnical side, where we use 70% slag in shallow soil mixing. And also, interestingly enough, we used 50% slag in the precast tunnel lining, concrete precast tunnel lining. And I know there'll be other discussions about precast and so forth, so I don't want to get into that too much. But I will say this was an interesting use of slag cement in the precast tunnel lining, in that there was a 150-year life cycle that we had to try to identify for the precast, and the winning mix used 50% slag to achieve that, and part of that being because of the low permeability that we could then factor into the durability analysis. But today we want to talk about more of the geo side, the 70% slag and the shallow soil mixing. Next, please. So this is a great picture of the tool itself. So think of it this way. You know, the ground was there, nothing was done to the ground. The contractor shows up on the ground site with this particular tool, which is a large cutting tool, which he then drives into the ground by hydraulically, and then running down the center of the tool is where we put the slag cement, bentonite, and Portland cement mixture. Then the tool reaches the target depth. It then reverses out as it is mixing that cementitious material in. And the real issue when we started this was, well, what should that mix look like? Next, please. So we spent quite a bit of time in the lab trying to figure out exactly what we could do and why we should do a few things. This first slide shows the target was 300 kilograms per cubic meter. So we took the native soil that we were trying to solidify and ran 4 or 5 different mixes. The control you can see is on the left, and that's 0. So that was 100% Portland cement. Then we tested 35, 50, and 70. We ran it up to 70 because this was also a DOT project, and 70% happened to be where their specification allowed us to use up to 70%. So we didn't want to go above that, though, as I said in the earlier slides, in this particular application, 80 and 85% is also used quite often. So you can see the 7, 14, and 28-day results, and not what most people would expect. But look at the water cement ratio. extremely high water cement ratio. And it's also in the soil, the in situ soil. Next, please. So we very quickly realized that we could reduce the total cementitious amount and still end up within at the desired results. So we then redid everything at 250 kilograms per cubic meter. Again, water cement ratio of 2, no bentonite, no water reducer, and just the natural soils. And here you can see that we were still well above target. Interestingly enough, the 100% Portland cement didn't really move that much. It stayed roughly where it was. And for numerous reasons. You could hypothesize the organics, every bit of the soil changes. We do know as the soil levels have higher organics in it, it hurts Portland cement more than it does slag cement. And typically, one of the reasons you can consider that is, again, the slag is very glassy and absorbs water much slower, not much slower, but slower than the Portland cement. So 7-day, 14 and 28 days, we were targeting, I believe, 800 PSI, and we were well within that target range. So the decision was simply the lower total cementitious, the 250 kilograms per cubic meter, and 70% slag. Next, please. The next project I wanted to touch on was something we did in Sanford. This was an old gasification plant where they had lots of heavy metals in the ground, and they were looking for a way of tying up those metals. This was also a Superfund site, I believe, as well, too. So in this particular slide, you can see the tool, and that tool is very similar to the other tool I showed you, is spinning down into the ground, and then on its way up, putting in that slag cement mixture and allowing the whole area to solidify. The proof in the pudding, of course, is the test wells around the project site, proving that the lowered permeability of this particular mixture was keeping the target heavy metals tied up. So you can see the tool in the distance, you can see the plant there. That is a slag silo and a Portland cement silo. Next, please. So this next project kind of ties up everything I've been talking about, and I get to repeat some of the good stuff to you yet again. So this is the Jade Signature project in Miami, downtown Miami. So every bit of concrete in this project contains slag. We of course are going to focus in more on the geo side, but it's of interest how this project has evolved. The first part of the project clearly was deep soil mixing. That was 13,000 tons of slag used at between 80 and 90% and 20 to 10% Portland. That range was simply, I'm not quite sure why they settled on two different regions. I think they were concerned about early strength. So some of the edges were done at 80, but the center part of the project was all bumped up to 90%, 10%. Then once that was completed, mass concrete then was put into the hole that was dug after the deep soil mixing, and that was mass concrete at 10,000 psi, where we used 60% slag, total cementitious of 1,040 pounds. What we're seeing in southern Florida is that because slag is widely available now, most of the mass concretes are moving towards slag for temperature control, but they can also achieve higher strength. So in my mind, that's always an oxymoron when you have mass concrete at high strength, because it's an exothermic reaction. The more strength you generate, clearly the more heat you've also generated over time. So traditional mass concrete, 3,000 and 4,000 psi is what I grew up doing. And suddenly now we have 10,000 psi, and we are doing projects where they want 12,000 psi concrete. And then of course, once the project is done, we move to the superstructure, and all of the material in that structure between 3,000 and 8,500 use slag at between 50 and 60%. Next slide. So this slide bears a little closer looking at from the geotechnical side. If you look at the edge of the building, you can see the tool marks, and you can see it looks like there's a beautiful wall standing there. So before this picture was taken, the entire work area, using that, that standard tool where they injected slag cement and Portland cement into the ground to solidify the whole area. Again, with low permeability, that took care of the water, and then they would simply dig out the parts where they needed to go deeper. And that's what you're seeing here, where the mass concrete would be. So what we're seeing in this application from a geo perspective is that we suddenly are now being, they're now making more underground parking in downtown Miami, for example, because they have a method of doing it. In the past, if they wanted to build an underground parking structure, they would ultimately have to dewater the ground. They would do a trench around the whole project where they would use tremie concrete or concrete that would solidify underwater to make walls around the structure and use that lower permeability, and then pump it out and dig out the center. This is kind of a different movement from that, in that the entire ground is solidified, not just the edges. And then, like a reverse computer chip, you dig out the material where you don't want it and do whatever needs to be done, whether it's a mass concrete element or some other concrete element can then be put in. So an interesting use that is well within kind of Slag's technical parameters of being able to achieve low strength with very small amounts of material that is perfect for these type of applications. Next, please. So the last project is, again, what we wanted to talk about, where I started. This is where I started in Slag Underground, and it's fitting to end here. So what they're doing is there's a large chamber that I will show you on the next slide that they need to fill up, and they wanted to fill it up in the most economical fashion. So what they do is they do the waste material from the mining process is called tailings coming out of the mill, that they then re-fluidize, pump with slag and Portland cement, and place that underground to again achieve that low strength with low cementitious values that they need to shore up the mine itself. Next, please. So I would point out that this project actually won a Slag Cement Association Project of the Year. So you can pull this project up on our website and get more of the details, but the details are very similar to the other things I'm showing. I think the mixed design was between 75 and 80% slag, and they were looking for relatively low strength, though they did achieve some high strengths in some areas where they wanted it. But they're more concerned about the flow and the adverse conditions that the concrete would be in, i.e. heavy organics and things like that in the mine site. Next, please. Another view of that, and in this case it was 90% slag is what we're showing, but I think the project will also talk about various mixes they used in various places. Next, please. Well, I think that's it. So I'd love to address questions.
Thank you, Gordon. I am just double checking to see if there's any questions. I don't see any at the moment. Give just a few seconds to see if any questions come in. Okay, it looks like there is no questions. Please remember to fill out the brief feedback survey that you'll see as you exit the webinar. A recording of this webinar will be made available on the SCA website in the following weeks. Please visit the SCA website at slagcement.org for more information on this topic. There you'll find almost 30 technical fact sheets, the slag cement PCR, EPD, and LCA calculator free to download. Thank you for attending today's webinar, If you haven't done so already, check out the other great webinars scheduled throughout the summer. Thank you and have a great day.